We begin with a clear purpose, a mission to understand the intricate workings of the natural world, and our focus is not merely to observe life, but to comprehend the underlying principles that govern it. The tick, an organism often overlooked or dismissed, provides a perfect subject for such an inquiry. It may seem an insignificant creature, a mere speck in the vast tapestry of life. Yet its influence extends far beyond its diminutive size, capable of shaping the health of individual animals, the dynamics of entire populations, the very character of the habitats they occupy. This is the story of how a single tick's bite, a seemingly minor event, can set in motion a chain of consequences that ripple through an entire ecosystem. Our journey will be one of scientific exploration, framing each observation within the logic of cause and effect. We shall investigate how the tick's unique biology and behaviors are not random occurrences, but precise adaptations honed by millions of years of evolution. To understand the tick's role, we must first identify it clearly. Ticks belong to the class Arachnida, making them relatives of spiders, scorpions, mites, not insects, and this distinction is crucial as it underpins their fundamental biology. For instance, adult ticks possess 8 legs, not 6. Their bodies are small, oval-shaped and flattened, a design that allows them to move easily through fur and feathers. Before feeding, an adult tick may measure only a few millimeters in length. However, its body is remarkably elastic. After gorging on a blood meal, a female can swell to many times her original size, becoming a grey engorged sphere, a living larder of nutrients essential for producing the next generation. Their global distribution is a testament to their adaptability. Ticks are found on every continent, even Antarctica, where they parasitize seabirds. They thrive in a wide array of environments: dense, humid, leaf litter of temperate forests, tall grasses of open savannas, the arid scrublands of deserts. Some species are host-specific, having evolved to prey on a single type of animal, such as birds or reptiles. Others are generalists, capable of feeding on a diverse range of hosts, including mammals, birds, and even humans. This flexibility is a key causal factor in their success. The tick's hunting strategy is a masterclass in energy conservation, a behavior perfectly attuned to its physiology and environment. Unlike an active predator that expends energy in pursuit of its prey, the tick is an ambush hunter of supreme patience. Its primary technique is known as questing. To do this, the tick climbs to the top of a blade of grass. To do this, the tick climbs to the edge of a leaf. This behavior is triggered by environmental cues, like increasing daylight. This behavior can also be triggered by humidity. It then anchors itself firmly with its rear pairs of legs. It extends its front pair into the open air, waiting. This posture is not one of rest, but of high alert, a living snare set for an unsuspecting passerby. The cause is a need to conserve energy. The effect is a hunting method that relies on the host to do all the work. This waiting game can last for an astonishingly long time. A tick can survive for months, in some cases over a year, without a meal, thanks to its extremely low metabolic rate. It enters a state of near-suspended animation, life processes slowed to a bare minimum. Lacking eyes in the conventional sense, the tick navigates a world not of light and images, but of shadows. The act of a tick feeding is not a simple bite, but a sophisticated and prolonged process of biochemical manipulation. Once the tick has selected a suitable location on its host, it begins an intricate surgical procedure. It uses its chelicerae, a pair of microscopic serrated cutting appendages, to slice open the skin. It then inserts its hypostome, a barbed harpoon-like feeding tube, deep into the wound. The backward-facing barbs on the hypostome act as anchors, making the tick incredibly difficult to dislodge. For many species, this physical anchoring is further reinforced by the secretion of a cement-like substance that glues the tick's mouthparts firmly in place for the duration of its meal. This secure attachment is only the first step. The true genius of the tick's strategy lies in its saliva, a complex cocktail of bioactive molecules that it injects into the host throughout the feeding process. This saliva is the key to its success, a chemical toolkit designed to overcome the host's natural defenses. One of the primary components is an anticoagulant, a substance that prevents the host's blood from clotting around the feeding tube. This ensures a free and continuous flow of blood, allowing the tick to feed uninterrupted for several days. The production of this chemical is a direct evolutionary response to the problem of blood coagulation, a fundamental barrier to any blood-feeding organism. Furthermore, the saliva contains powerful anti-inflammatory compounds and vasodilators. The vasodilators cause the host's blood vessels near the bite site to widen, increasing blood flow to the area and making the meal easier and quicker to obtain. The tick's role in the ecosystem is far more complex than that of a simple parasite. While it draws life from the blood of its hosts, its influence radiates outwards, affecting populations' behaviors and the flow of energy through the food web. As direct parasites, a heavy infestation of ticks can have severe consequences for an individual animal. The constant loss of blood can lead to anemia. The constant loss of blood can cause weakness. The constant loss of blood can reduce fitness. The physical irritation and skin damage from numerous bites can cause stress. It can also cause secondary infections. The ultimate effect is a decline in the host's ability to survive and reproduce. It's a direct form of population control exerted from the bottom up. Ticks are reservoirs and transmitters for an extraordinary range of pathogens: bacteria, viruses, protozoa. These pathogens cause illnesses like Lyme disease, anaplasmosis, babesiosis. By moving pathogens between different hosts, from a white-footed mouse to a white-tailed deer and potentially to a human, ticks act as a critical ecological bridge. The spread of these diseases can have profound effects. Our scientific journey into the world of the tick reveals a creature of remarkable sophistication, a micro-predator whose influence belies its humble size. Its life is a testament to the power of evolutionary adaptation, where every biological feature and behavioral trait serves a distinct purpose. The strategy of patient waiting, the reliance on a multi-stage life cycle, the deployment of a complex biochemical arsenal are not accidents of nature. They are precise and elegant solutions to the fundamental challenges of finding food, avoiding detection, ensuring the continuation of its species. This is the clear, logical narrative of cause and effect that science seeks to uncover. The tick's role as a parasite and disease vector makes it one of the most consequential small animals on the planet. Its ability to regulate host populations, transmit pathogens across species boundaries, gives it a profound impact on ecosystem health and stability.